Good morning, everyone. I'm Anderson. I have been working for the GREYDIENT project since 2021. I work from ETH Zurich at the chair of risk, safety, and uncertain quantification. The topic of my research is uncertain quantification and reliability analysis for noisy gray box models, meaning that the goal of my project then is to develop a methodology that is robust and cheap to evaluate, reliable, to perform reliability analysis for these noisy or non-deterministic or stochastic models. They're all synonyms. Trying to be a bit more specific here, in reliability analysis, what we're concerned with is essentially quantifying the probability that the uncertainties in the system will lead to the failure of the system. And then when we are doing that, in my project at least, two challenges arise. The first one is that we want the probability of failure to be as small as possible, meaning that computing this probability of failure becomes quite expensive because we have to run many simulations of expensive to evaluate models. And on top of that, in the project specifically, we have these stochastic outputs, meaning that contrary to the usual models that we have, when we have one input, we get just a single output. In our case, in the project, one input will lead to a random variable as response. And then defining what reliability analysis is for this case is still, well, not yet well defined yet. To perform reliability analysis on that, then from the beginning of the project, we noticed that we had two different types of problems when tackling these non-deterministic models. The first one is what I'm calling noisy models here. In this case, the noise is it comes from an external source. So it comes from the data measurement or some data-driven system. And this noise increases the uncertainty of the problem, introduce uncertainty into the problem, which inflates the probability of failure. And that's not what we want. We want to actually compute the actual probability of failure of the system. To do that, we need to do the noising. And then we have been employing some machine learning approaches to that, namely Gaussian process regression. And we combined it with active learning approaches to increase the efficiency. So we sequentially enrich our training set so that we call the expensive to evaluate function as few times as possible. This method is done and it will be soon published. And with this approach, we can perform reliability analysis for models with either computational noise or even data-driven models. Indeed, like from data, we can perform reliability analysis. Then the second type of problem that we are tackling is what I'm calling here stochastic simulators. In this case, the noise is intrinsic to the problem, and we want actually to see how this noise will affect the probability of failure. So I like to bring the example of wind turbines. The load of wind turbines are essentially winds, and they are random. We cannot get rid of this randomness of the wind, and we want to quantify how this randomness will affect our probability. To do that, we use surrogate models, meta models that have been set in this morning, that are called the stochastic emulators, so surrogates that comply with the stochasticity of these models. And we perform reliability analysis on them because they are cheaper to evaluate. Right now, we are developing an active learning approach for them so that we increase the efficiency of the methodology. And once this is ready, it can be used for engineering design of any kind of model that can be cast as a stochastic simulator, such as the wind turbines or even structures under earthquake load, these kind of things. And of course, we can use it for RBDO and everything that we need reliability analysis of. Essentially. That's it. Thank you for listening.